For consideration of a steady heat conduction in a plane walls, we can start with an example. Imagine a house in a winter. As you may know, we have heat loss through the wall of the house from inside to outside. This is because of the temperature difference in two sides of the wall. We consider this example as a steady heat conduction because temperature inside the house and temperature outside of the house can be assumed as a constant value, and it is a one-dimensional heat transfer because, as you can see also in this figure, the temperature at the surface of the wall, at inside or outside of the wall in y direction, and also the temperature in the z direction is almost constant. So as you may know from the previous sessions, heat transfer is due to differences in the temperature. So we don't have any temperature difference in this direction, so we don't have any heat transfer in those directions. Moreover, the thickness of the wall in x direction is much lower than the other two directions. So the heat transfer in this direction will be much higher than the other two directions. By this assumption, we can write the heat balance for the wall of the house. And also you should know that we don't have any heat generation in the wall. So we can write this equation for heat balance of the wall. The heat which is the rate of heat transfer to the wall in this direction minus the rate of heat transfer which goes out of the wall will be equal to changing the thermal energy of the wall. But as I told you, we don't have any change of the thermal energy of the wall with time because we are considering this example as a steady operation condition. So this term will be equal to 0. It means that rate of heat transfer into the wall will be equal to rate of heat transfer out of the wall. And in other words, we can write this equation as well. It means that rate of heat transfer by conduction through the wall is constant. With this information and using the Fourier law of conduction heat transfer for the plane wall, we can write rate of heat transfer, conduction heat transfer through the wall like this. It will be equal to a minus average thermal conductivity of the wall times the surface area of the heat transfer times the change of the temperature in x direction, dt divided by dx. And we know that dt divided by dx is constant. So the temperature through the wall varies linearly with x. You can see here the wall with this condition. At the inner surface we have T1, at the outer surface we have the T2. Then the heat transfer or Tx, which is the temperature of the wall in x direction, is dependent on x, and it changes linearly with the change in the x. By rewriting the above equation and rearranging, bringing x to the left side of this equality by integration from x0 to xl, x0 here, that temperature at this point is T1, to L, that temperature at the L is a T2. We can write this integration equality. By integration of this equation, we will reach this equation, final equation for the conductive heat transfer through the wall. And as you can see here, this heat transfer rate is dependent on the average thermal conductivity of the wall, surface area of the wall, temperature difference between the two sides of the wall, and also it is inversely related to the thickness of the wall. By increasing of the L, the heat transfer rate to the rate of heat transfer by conduction through the wall will decrease. And also we can use this equation to calculate temperature at each point in x direction for each Tx by substitution of x or temperature at T2 position. Finally, we can use this equation for rate of heat transfer through the wall for steady operation condition and also one-dimensional heat transfer. we found this equation for heat conduction through a plane wall. By rearranging of this equation, we can write this equation. This new term in the equation is called thermal resistance of the wall against heat conduction, or simply we can call it conduction resistance of the wall, and it is dependent on the thickness of the wall, thermal conductivity of the wall, and surface area of the wall. This equation of heat transfer is similar to the equation of electric current flow, as you can see in this figure. Now consider convection heat transfer from a solid surface of area AS in this figure, as the temperature of the surface is Ts, to a fluid whose temperature sufficiently far from the surface is T infinity. We will have this equation, which we call that Newton's law for cooling, which is actually equation for the convection heat transfer from the surface to the surrounding, and each is convection heat transfer coefficient. Then it is easy to show this equation by rearrangement of the Newton's law of cooling. Then we will have same equation like conduction heat transfer for convection heat transfer, and we can again find this thermal resistance for the convection, or which is thermal resistance of a surface against convection, or simply it is convection resistance. But when the wall is surrounded by a gas, the radiation effect also cannot be neglected, and we should also consider the effect of radiation on the heat transfer. In that case, the rate of radiation heat transfer between the surface of emissivity of epsilon and area of the A at temperature of Ts and the surrounding temperature, a surrounding surface at some average temperature of the surrounding can be expressed as follows. By rearrangement of this equation, we can reach this final equation, which is only dependent on the difference between the temperature of the surface and the surrounding, and these new concept that we can call that radiation resistance, and it is equal to 1 divided by radiation heat transfer coefficient times the surface of the heat transfer. And finally, we can reach this equation for the radiation heat transfer coefficient. Just notice that Ts and T surrounding should be in term Kelvin to calculate H radiation. The definition of the radiation heat transfer coefficient enables us to express radiation conveniently in a similar manner to convection in terms of a temperature difference. But H rad depends strongly on temperature, while H convection usually does not. This can be seen by comparing these two equations for H rad, which is the radiation heat transfer coefficient, and the previous equation for the convection heat transfer coefficient. Sometimes a surface is exposed to the surrounding air, involve convection and radiation. As you can see in the figure, we have two kinds of heat transfer for the surface: heat transfer due to convection and also radiation. So the total heat transfer at the surface is determined by adding or subtracting when the heat transfer direction is opposite each other for the convection heat transfer and radiation heat transfer. These convection and radiation resistance are parallel to each other and may cause some this complication for thermal resistance calculation. Only when the surrounding temperature of the surrounding fluid near the surface is equal to T infinity. The temperature of the fluid who's far enough from the surface are equal. The radiation effect can properly be accounted for by replacing H in the convection resistance relation. Then we will have this form of the heat transfer coefficient that we call that combined heat transfer coefficient. It is a combination of the heat transfer coefficient for convection plus radiation heat transfer coefficient. Now let's consider steady one-dimensional heat flow through a planar wall of thickness L and with thermal conductivity of K, which is exposed to the convection of both sides, with the temperature of the fluid at the both sides are T infinity 1 and T infinity 2. As you can see also in the figure, we have three types of heat transfer for these media. We have convection at the left side of the wall, we have conduction heat transfer through the wall, and we have convection heat transfer at the right side of the wall. By assuming T infinity 2 here lower than T infinity 1, the heat transfer graph be something like this. And also we know that the heat transfer coefficient of the fluid at each side of the wall are H1 and H2 for H1 for the left side and H2 for the right side of the wall. Then to calculate the total heat transfer through the wall, we should calculate the thermal resistance of all of these three parts. And also notice that rate of heat convection into the wall is equal to rate of heat conduction through the wall, and it is also equal to rate of heat convection from the wall. Then we can write this equation for the equality of the heat transfer or heat balance through the wall. The convection at the left side of the wall, H1 times A times T infinity 1 minus T1. Convection, these equations are according to the different type of heat transfer into the wall, through the wall, and from the wall. Heat transfer into the wall is convection heat transfer, and we can use this Newton's law for convection heat transfer. And also for the right side of the wall, which is from the wall, we can write this equation. And heat conduction through the wall is according to Fourier's law of heat transfer. We can write this. K is thermal conductivity, A is surface area of the heat transfer of the wall. T1 and T2 temperature at the both side of the wall, and T infinity 2 temperature of the fluid at the right side of the wall, and the T infinity 1 temperature of the fluid at the left side of the wall, which is enough far from the surface of the wall. Then by rearranging this equation, we can have this equation, the temperature difference divided by these terms, that according to previous sessions or slides, you know that this term here is equal to convection thermal resistance. This term is equal to the conduction thermal resistance, and also this term is equal to convection thermal resistance for the right side of the wall. Then we can write this equation for all of the wall, that Q dot or heat transfer from the fluid at the left side of the wall to the right side of the wall can be written like here, that T infinity minus T infinity 2 divided by total thermal resistance. To have an overall heat transfer coefficient, it is convenient to express heat transfer through a medium in a similar way like Newton's law of cooling, like this equation. Q is the overall heat transfer, which is equal to UA delta T, which U is the overall heat transfer coefficient and delta T is temperature and A is the surface area of this heat transfer. So it is convenient if we just have this U, we can calculate this Q or heat transfer for the medium. So, and also this UA is equal to 1 divided by total thermal resistance of that medium. So for a unit area, the overall heat transfer coefficient is equal to the inverse of total thermal resistance. So the overall heat transfer can be calculated only by knowing the total thermal resistance. And notice that we don't need to know the temperature of the surfaces of the wall to evaluate the rate of steady heat transfer through it. Only we need to know the convection heat transfer coefficients and the fluid temperature on both sides of the wall. It means we need H1, T infinity 1, and H2, T infinity 2 to calculate this heat transfer. But we can still calculate the surface temperature by describing this thermal resistance concept. By taking the surface at which the temperature is to be determined as one of the terminal surfaces. Now let's consider heat transfer through multi-layer plane walls. In practice, we often encounter plane walls that consist of several layers. The thermal resistance concept can still be used to determine the rate of steady heat transfer through such a composite wall. The walls, which are made of different material, usually called composite walls. As you may have already guessed, this is done by simply noting that the conduction resistance of each wall is equal to L divided by Ka, which are connected in series, as you can see in the figure. By dividing temperature of two surfaces at known temperature by the total thermal resistance between them, we can calculate heat transfer through this composite wall. For example, you can see in this figure two-layer composite wall. The total thermal resistance for this wall consists of 4 different thermal resistance. 2 of them are convection thermal resistance and 2 of them are conductive thermal resistance. According to previous slides, you know that convection thermal resistance for the left side or for the surface at the left side of the wall and fluid with the temperature of T infinity 1 is this much, while the conductive thermal resistance for the material 1 is L divided by K1A. L is the thickness of the wall, K1 is the thermal conductivity of the wall, and A is the area of the heat transfer of the wall. Material number 2, again the L2 is the thickness of the material number 2, and K2 is the thermal conductivity for the material for the part 2 of the wall, and A is the heat transfer area. And the convection thermal resistance at the right side of the wall is 1 divided by H2A, which are related to the fluid at the right side of the wall. We could also find this value by following the approach already used for single layer case, by noting that rate of steady heat transfer or Q dot through a multi-layer medium is constant, and thus it must be the same through each layer. Note from the thermal resistance network that the resistance are in series, and thus the total thermal resistance simply the arithmetic sum of the individual thermal resistance, as you can see here in the path of the heat transfer. This result for two-layer plane wall is similar to the single layer case, except an additional resistance which is added to the equation, which is related to the material number 2 for the wall. This result also can be extended for 3 or more layer plain walls by adding additional resistance for each additional layer. Once Q dot is known, we can calculate temperature at the surface of each layer of the wall. We can use this equation to calculate the temperature at the point J of the wall, which Ti is known. Total thermal resistance between I to J is also determined, and then we can calculate temperature at the surface of that layer by using this equation, where Ti is a known temperature at location I, and our total Ij is the total thermal resistance between location I and J. For example, when the fluid temperature T infinity 1 and T infinity 2 for the two layer case shown in figure, T infinity 1 and T infinity 2 shown in this figure, for the two layer case are available, and Q dot is also calculated from the above equation. The interface temperature T2 between the two walls can be determined from this equation. You can see here how we can calculate the temperature at each interface. Here we are going to calculate the temperature T2 as the interface between the material number 1 and material number 2. As you can see here from the previous equation, T infinity 1 minus T2 divided by total thermal resistance between I and J, which is a summation of convection thermal resistance of this part and the conductive thermal resistance of material number 1. Then by substitution of the values for these two thermal resistance in the equation, we will have this equation. By rearrangement, we can find T2. Same calculation or same procedure can be used to find temperature at each interface. To find T1 or temperature at this interface, we can use this equation. At interface 2 or T2, we can use this equation, and for the temperature at the interface 3 or T3, we can use this equation. And as you can see in this equation, we should put the total thermal resistance to that point, or between the thermal resistance between Ti and Tj. Here Ti is T infinity 1 and T1. For the T2, T infinity 1 is the Ti and T2 is Tj. And thermal resistance between I and J is the summation of thermal resistance of convection and conductive thermal resistance of the material number 1 of the wall. And to find the T3, we can calculate from the right side. Then Ti is T3 and Tj is T infinity 2. Again, we can use this equation to calculate T3 because T infinity 2 is known, and thermal resistance from I to J is also known, which is a convection thermal resistance between these two.